Welcome, everybody. All right, I think we are live. Um, you can send me messages in the chat if you have questions or to submit answers when we stop for that kind of thing. I am going to, as before, go through the worksheet and talk a little bit about matter and chemical and physical changes. We'll see how far we get today. Probably about halfway through, and then we'll have another stream later this week. As usual, I will also be monitoring the live stream Discord channel, so if you want to join in there, you are welcome to. All right, please let me know if anything weird happens, like if the stream cuts out or there's some sort of problem, because I often can't tell on my end. All right, let's get started. So, all right, last time we talked a little bit about the scientific method and measurements. Make sure you review that video if you haven't already. Today we're going to look at matter, types of matter, different ways matter can change, and how we differentiate physical from chemical changes. We'll be doing a lab about this also starting next week, since the second group still has to do the first lab this week. All right, so matter is anything that has mass and occupies space. So objects we think of as made of matter, right? I'm sure you can find an example of something that is not air, water, a brick, or you. There's a lot of other things around. We often have some issues categorizing matter because there are different ways to classify it depending on how you see it and what's happening with it, how it's being used. Excuse me, sorry. I'll turn my light down a little bit. Okay. So for example, we can look at water from a macroscopic perspective. That is, what does it look like to us as we experience it? We can also look at what we would call a microscopic or molecular picture, really submicroscopic, since atoms are a little smaller than that, but and kind of talk about what the atoms themselves or the molecules are doing. Yeah, just shift this around a little. Sorry, still getting used to this system here. All right, so for example, water. We use water as an example, even though it's a fairly distinct substance, like it's a substance that's very different from a lot of other things. It's a unique substance. It's something that we experience all the time, so it's a good example just because we have experience with it. So we see water as steam or water vapor, water as a liquid state, and ice as a solid state. We should also note that actually the gas form of water is, make sure this is working here. Steam is not a wrong way of classifying it. It is steam. We also call it water vapor. The thing that gets a little bit confusing, or sometimes that people mistake, is water vapor is actually completely colorless. You can't see it at all, which is not our experience with steam, right? We can see, you boil water or something, you see the steam. Well, what you're seeing is not actually water vapor, but it's water vapor quickly turning into liquid water, tiny, tiny droplets of liquid water, and that's what's refracting the light or reflecting the light and what's making us see something. The actual vapor itself, you actually can't see. So we've got the three phases of water. If we zoomed all the way in and we were actually able to see the molecules, we would see different amounts of interaction and separation. So you'd see water, and there's actually a problem with this picture that I want to talk about. So you'd see, first of all, let's look at the solid. solid water is an ordered structure. So the important part of this picture is that it is ordered, that you have a regular arrangement of molecules that is repeating and crystalline. And we'll talk more about those interactions and what holds that together later. You can see there's some holes here. That's because of the shape that water molecules pack in. There's actually some space left in between there. And because of that, liquid water, is actually more dense than solid ice. And we'll talk about density in a little bit, but basically the liquid takes up less space than the solid. If you have ice cubes in your water and the ice cubes melt, the overall level is actually going to go down because ice takes up more space than water. And that's really unusual. Most substances, not all, but most substances, the solid is the most dense phase, and then liquid is a bit less dense, and then the gas is the least dense. But water, that's actually flipped. Liquid is the most dense phase, then solid, and then the gas. So the other way we can think about this is the interactions of the molecules. In a solid, the interactions are generally at their strongest. So even though the overall structure is less dense, the interactions between the water molecules are at their strongest in ice. That is still true. In water, there are interactions as well. In liquids, there are generally interactions between the molecules. In a gas, sorry, you can't even see this. Let me move that up. Sorry, I keep forgetting that my head is there. To move it over. In a vapor, in a gas, the molecules are completely separate from one another. There is essentially no interaction. As you probably notice, when I talk about chemistry, I don't like to use absolutes because there's lots of exceptions and there's lots of nuance about what's really going on. But I also don't want to confuse you and say, well, it's kind of like this, but it's not really like this. So I'm saying things like there's effectively no interaction between water molecules, although depending on temperature and pressure, there can in fact be some interaction, but we're going to assume there's no interaction there. So totally separate, lots and lots of space in between molecules. In fact, the scale here is way off. In a gas, there is so much space between the molecules that the size of the molecules end up kind of not mattering because there's just so much space in between them. So because of that, we can define these phases based on the way that they behave. So one common way that these states are distinguished from each other is by their shape and their volume. So for instance, if you look at a solid, the shape is fixed. It doesn't matter what you do with that solid, where you put it, it's always going to have the same shape if it's a solid. Whereas a gas has no fixed shape. Whatever container it's in, whether it's a beaker or a balloon or whatever, it's going to take the shape of that container. So then where does liquid fit in here? Would you say that liquid has a fixed shape or liquid takes the shape of its container? If you want to drop that in the chat here for anyone who's listening. Does liquid water have a fixed shape or does it take the shape of its container? Container. Yeah, right, exactly. Thanks, Alyssa. So I'll just do that. Water also takes on the shape of its container. All right, so what about volume? Volume is how much space it takes up overall. Now, a solid also has a fixed volume, but a gas kind of strangely, not really strangely, but takes on the volume of its container. If you have a certain amount of gas in, let's say, a balloon, and that balloon has a certain amount of volume, that's how much volume of gas you have in there. And if you were to compress that balloon and like squish it, you would have actually a different volume of gas. You still have the same mass, you still have the same amount of matter inside there, but it now takes up a different volume. So it takes up a different amount of space. And that's because of all the space in between the molecules that it can be so heavily compressed. So what do you think about water? Can water be compressed, or does water have a fixed volume? Or liquid, sorry. Do liquids keep their volume, or do liquids change their volume as the container size changes? What do you think? So fixed volume. So you're less sure about that one because there's a question mark. Anybody else want to jump in? What do you think? Is it a fixed volume, or does it change with the container? Nobody else wants to play along? All right, that's fine. It also has a fixed volume. So you can see here that a gas takes on the shape of its container and the volume of the container. A solid, both are fixed, but in a liquid, we take on the shape of the container, but we have a fixed volume. So sort of one of each. All right. So we've talked about most of these. I'll leave you to look up the specifics for those, but you can probably figure it out from what we've already said. One thing that we should note, and we'll define this a little bit later, changes between states are physical changes only. So that means that the substance itself, what it chemically is, which again we'll define in a little bit, doesn't change when we go from solid to liquid to gas. So if you have water in a solid, you melt it, you still have water, just in a different phase. You vaporize it, you still have water, but in a different phase. At no point during those operations would you actually split up a water molecule into, say, hydrogen and oxygen atoms or something like that. So the way we would write this chemically, you can see this example here. Something of a chemical reaction. So it's not really a reaction and it's not chemical, it's actually a physical change, but it looks like a chemical reaction because we've got chemicals on one side and an arrow and something on the other side. But the way that what this is really saying is this is an L for liquid water, and this is an S for solid water. And we're saying that the water is transforming from a liquid to a solid. So that's actually a physical change. And when you describe this on your sheet, please describe it at the molecular level. So what's happening to the actual molecules or the little particles? Sorry, I'm trying to talk and write different things. That doesn't work. Okay. So try to describe that at the molecular level, what's really happening there. All right, and then we're gonna do this one together a little bit. So thinking about how they relate to their container, what would happen? What would you see if you tried to fill a balloon with each state of matter? If you fill the balloon with each state of matter, what's happening? So just pick one, whichever one is maybe easiest for you, or whatever one you want, and just let's see what you think. What do you do if you fill a balloon with a certain state of matter? Oh, I got your message, Anna. That's okay. You can be behind. That's fine. All right, hold on. I have to. How do I do this? All right, I have to take a minute. I'll be right back. Okay, sorry, I'm back. Um, yeah, yeah. Sorry, that doesn't make sense. So like, um, actually, you know what? Let's skip these. I don't want to talk about that because the issue is that the balloons are a little bit tricky because of how they expand fairly easily, regardless of what's in there. So let's actually skip that. Let's go on and talk about a piston. That's a little bit um, so a piston or a syringe, right? You've got like a fixed. Let's draw this if you don't know what I'm talking about. So you've got like a fixed tube, and then there's a sort of a plunger inside that can be moved up and down, right? So I mean, so you know, but um, let's say we cork or stopper off this bottom, so nothing can come in or out. All right. So if you fill it with gas, can you move the piston back and forth? And the answer there is yes, you can. And if you tried this, you would see that what would happen is there'd be some resistance there. You'd have to, use some force, but you can actually change the volume of the piston, um, even though you haven't added or subtracted any air or any gas. Let's say it's air. So you can compress the gas, you can compress the air. You can also decompress the air by pulling the piston out and actually lower the pressure inside there. So you can do both of those with a gas. But if a piston's filled with rocks, you can't, right? You can't push the rocks to take up less space because they take up a fixed amount of volume, a fixed amount of space. And it's actually the same thing with a liquid, even though you could argue there's a very slight compressibility with a liquid, but that's really how hydraulics work. If you've ever dealt with those sorts of things, in hydraulics, you're using pressure to force liquid into some sort of a space, and because the liquid can't be compressed, you can then do work by expanding something else. So you can squeeze water at high pressure into a different place and then use that to do work to like expand something or push something or pull something or whatever. All right, so now we're going to do an activity together. And again, if you're following along, if you've got the worksheet, if you can fill it out, you don't have to type your answers in the chat if you don't want to, but it's nice if we can get a little bit of interaction in here. So here's a table that just kind of talks about, or that just gives some data on some different substances and introduces some terms that you may or may not know, and that you may or may not know the correct definitions for. So, for example, we have four, or not for example, but we have four categories here. We have item, classification, state, and formula. The items are some different items: aluminum, hydrogen, water, table salt, salt water, coffee, and some muddy water. And these are the classifications for those things. So aluminum and hydrogen are called elements, water and table salt are called compounds, salt water and black coffee are called homogeneous mixtures, and muddy water is called heterogeneous mixture. And don't worry about what those terms mean yet. We're going to actually try to figure out the definitions on our own based on the data we have. So here are the states, which we've just talked about. one state that we haven't talked about yet is aqueous, which means dissolved in water. So, well, you may or may not have heard that term before. And then the chemical formula or formulas. So how would we express the chemistry or the atom components of these substances? All right. So just looking at those, let's see if we can answer some of these questions. So first, consider this model. This is our model. How does the formula of an element differ from that of a compound? So now I'm not asking you like use your former knowledge to figure that out or to memorize that definition, and I'm not asking you to look this up. I'm asking you to just look at this table and see if you can figure out the difference between the things that are labeled as elements and the things that are labeled as compounds. So looking across the table, can you find something that distinguishes those? So how is the formula of an element from these first two columns different from that of a compound? What's a difference that you see in this table looking at the other columns? All right, good. Compounds have two capital letters. So what do you think that means? That's correct. We've got the compound. This one has an capital H, capital O. This compound has a capital N and a capital C. And these only have one. So yeah, that designates something about the parts, that we've got some multiple parts in a compound and only one in an element. So what do you think is another name then for that part? See if anyone else is joining in here. Yeah, exactly. That part is an element. So an element is made of one kind of thing here, and the compound is made of maybe two kinds of things. We might want to generalize that out a little bit more later, but for now, that makes sense. So then, if you were to think of a more general rule, how can you distinguish elements from compounds based on their chemical formulas? Well, one way we might generalize this then is to say elements have one type of atom, compounds have, and based on the data, we might just say two, because that's all we've got so far. But I'm just going to tell you it's actually two or more. Um, and then we should also specify that compounds have two or more types of atoms in the formula. Because if we go back up to the table here, we can see some other stuff that also has two or more types of things, but those are not called compounds. Those are called homogeneous or heterogeneous mixtures. So it can't just be how many atoms there are, but something about that they're in this formula together. You know, they're missing this word and so the next thing is going to help us out with that a little bit. How does a pure substance, the element or the compound, differ from a mixture? So we're getting a little extra information here. They're telling us that elements and compounds are both called pure substances. And this is something that I've noticed messes people up a little bit sometimes. Elements are very obviously pure because they're only made of one kind of thing. But compounds, it's a little bit tricky because they're made of multiple atoms, but they're still pure substances because those atoms are put together in this chemical formula. And so, how does a pure substance differ from a mixture? Well, we can go back up here again. When you're working through these types of things, you shouldn't have to look this stuff up. You should be able to just use the model, use the table, the data to figure this out, to construct the knowledge for yourself. So in this case, the thing that I most notice is the word and. All the mixtures contain this word and when we're talking about the chemical composition, whereas the pure substances don't. So mixtures then must be made up of multiple elements, compounds, things like that, put together in some other kind of a way. And you can look up these. You can probably figure that out too, because they're right here in the table, and the states are given there. So then let's put this all together. And here, you know what I'm going to do? I'm going to make myself smaller so that I stop covering stuff up here. Because there we go. Okay. So now, let's take a look at this table. Pure substances versus mixtures, and how we define them. And this is a good way to kind of summarize all the data together. Pure substances composed of only one type of atom or molecule. And you know what? I'm going to put that kind of in quotes because, again, that's not quite right from the chemistry standpoint. There are other things that are pure substances that are not molecules. Um, they're called extended solids, for instance. So big things that kind of keep going in all directions. And then mixtures are going to be two or more different types of atoms or molecules. But there's another key here that should be up there, but is instead down here. But that's okay because we'll just highlight it. So if we're talking about different types of elements, different types of atoms or molecules, in pure substances, these things are chemically combined. And in mixtures, these things are physically combined. So that has to do with how the substances interact with each other. A physical combination is something like is a mixture. So you can think of it as something that's stirred together, that's dissolved, that's crushed together, that's physically put together in some way, as opposed to a chemical combination where atoms are actually bound together. And it might help a little bit if we look at these pictures. So an element here shows one single type of atom, and a compound shows one single type of molecule, but made of multiple types of atoms. And then the two types of mixtures both involve multiple types of, let's say, atoms or molecules. And the two types of mixtures are separated more by the visible separation within them, or the existence of domains that can be distinguished. So another way to say that, if you look at the pictures, a homogeneous mixture, everything is distributed evenly throughout. So the composition is the same throughout. And often, visibly, if we just look at it, we can't actually tell if it's a pure substance or not. So often there are, if we go back up here, let's take a look at an example. Black coffee. Black coffee is a mixture because it has lots of stuff in it. There's water, there's flavor molecules, there's color molecules, there's maybe sugar if you put some sugar in it, caffeine, whatever, lots of stuff in there. But if you just look at some black coffee, it just looks like one thing. It looks like a single substance. So that makes it a homogeneous mixture. In a heterogeneous mixture, we can clearly see the distinct parts of the mixture. And although I say clearly see, it's really not that clear because it depends on how you're looking at it. Are you looking at it like just on a table, or are you looking at it in a microscope? That may actually change whether you call something homogeneous or heterogeneous, and that's okay. Not every substance is going to be clearly put into one of those categories because it does depend on how you're looking at it. But something like let's say water with rocks in it would be very clearly a heterogeneous mixture because you see the rocks, you see the water, they're definitely different things. But I would say even up here on this table, we've got muddy water as a heterogeneous mixture of a liquid and solid. And sure, if you let it sit, you can definitely see that. But if it was really fine mud and you mixed it up really well, then, it might be a homogeneous mixture. So, I'm sure you've seen like dirty water that's kind of brown, that is not clearly heterogeneous. It might really look like just one thing, but that's just because of particle size and how easy it is to distribute those particles. So, elements should be pretty easy to distinguish generally. You can usually pretty easily tell of a heterogeneous mixture because it's got these different pieces in it. Where people mess up is generally these two because they look similar. And the other thing that messes us up here, kind of like last week with the laws and theories, is that compound is used in a non chemical context to mean mixture, which is just an extra layer of confusion. So if you get if you go to a pharmacy and they compound a medication for you or something, that means they physically smash it together or they mix it up in a cream. That is a physical combination, and that is not a compound. That's a homogeneous mixture. Um, we also use compound um, like like um, like if you're fixing the wall, you might put like a drywall compound or a spackling compound or something on it. Also, not a compound from a chemicals perspective. That's a mixture. So a compound for us always has to be a single pure substance that is made of atoms chemically combined together. So elements combined together. And I'm also going to cancel this, especially if I don't even do this in person, but especially being remote, you don't have to memorize the names and symbols of the elements on the periodic table. I really, there will be no point in this class where you will not have access to a periodic table. So don't worry about that. All right. So as an example, here are some compounds. These are some molecular formulas, although these aren't necessarily molecules. For example, this one, milk of magnesia, magnesium hydroxide, is actually a ionic compound, not a molecule. We should also notice this is in milk of magnesia, but like the actual stuff, if you've seen it, like the I don't know bottle of it, the antacid is actually a mixture because there's water in there. It's a suspension. You can see the compounds, even though they get fairly complicated, like here, C17H18F3NO, lots of atoms in there, but still one compound. The fact that it's given as a formula shows that these things are all chemically bound together. And so then I want you to go through and try to figure some of these out. Let's do a couple together, and then I think we'll stop and we'll do changes of state next time. So let's look at air. Is air a pure substance or a mixture? And if it's a pure substance, is it an element or a compound? And if it's a mixture, is it heterogeneous or homogeneous? So if you could just drop in a guess there in the chat or in Discord, is it a pure substance or a mixture? And then if it's a pure substance, is it an element or a compound? If it's a mixture, is it heterogeneous or homogeneous? Give everybody another minute to answer. Right. Well, depending on your experience and your expertise, we do actually perhaps need a little bit more information here. What is air made of? You may know that, you may not. So I'll tell you. Air is actually a mixture of gases. It is mostly nitrogen, which is N2. There's also oxygen there. There is carbon dioxide there. And there is water vapor in the air. Those are the main components of air. There are also some smaller, less populous components. But it is a mixture because it has all these individual pure substances mixed together. And that's what makes air. Air doesn't have a single chemical formula. So now, if we want to determine whether that mixture is heterogeneous or homogeneous, that's a little bit more subjective, but would we say that the air is fairly evenly mixed, or would we say that those components kind of occupy their own separate places within a sample of air? And I would say those are pretty evenly mixed. We don't walk into a room and the oxygen is on one side and the nitrogen is on the other side. We don't have little pockets of oxygen throughout the air. It's all pretty evenly mixed through. And so that makes this a homogeneous mixture because you can see, or you can't see, but because the air is evenly distributed, the substances are evenly distributed throughout the air. All right. And I'll leave these to you to figure out. If you're not clear about some of these, because again, we're not going to go through this entire document together, although I can go through it with you, we can do office hours or whatever if you want. But if you have questions about these or there's some that you aren't sure about, please ask because I want to make sure that you can do this type of classification. You should have some practice in the second mastering chemistry assignment to there should be some problems there where you can practice this classification as well. If you're routinely getting them wrong, please let me know because maybe there's some misconception there that we need to clear up before we go on into other stuff. All right. So maybe what we'll do, we'll stop there for now. I'll give you a chance to work through this stuff. And then for the next stream this week, we will we'll start by actually going through this whole table before we move on to talk about changes of state. So if you could try to fill this out either right now or sometime soon so that we can go through it. It's always best to go through answers of things after you've already tried it. So I would really recommend that you try it first and let me know if you have questions or problems. So for those of you on the chat while we're here, this is a good time. If you have other questions, other things that you want me to address in this format, you can always contact me on email or Discord also. But if you're right here and you've got a quick question, go ahead and I'll try to answer it before I go away for now. Make myself bigger. All right. Well, let me know if you have anything else. Otherwise, I will see you later this week. I think we're gonna try to do the next stream, maybe a Thursday evening, to try to catch some people who can't make it in the morning. So I'll see you then. Otherwise, I'll talk to you online. Bye, everybody. Thanks for tuning in.